Hey, good morning everybody. This is Mr. Ainsworth, and we're going to get into our fourth example here in linear programming, taking a look at how to handle a making crafts problem, basically a manufacturing problem. So let's check it out and let's read it together, translate it into a table here, and solve the problem together here. We got two artists. Their names are Bailey and Chloe, and they want to make some ornaments. They get $80 for each wooden snowman. All right, that's an income right there. Income meaning how much money they make, and it says $64 for each Santa Claus, so $60 for a Santa. Come on, what's going on here? So Santa Claus, there we go. All right, so that goes down here in the income section here. We can write down what they make. So $80 for one snowman, so $80 for a snowman, $64 for a Santa Claus. All right, that's great. On average, Bailey must work 4 hours and Chloe 2 to make a snowman. So these first numbers here refer to a snowman. Snowman's right here, so let's put those values in. So let me see, what do we have? So 4 for Bailey and 2 for Chloe. So 4 for Bailey and 2 for Chloe, and we're talking about hours here. All right, and that's in respect to a snowman. Now, Bailey must work 3 hours and Chloe 4 for a Santa Claus. So the second portion of it right here, this part, refers to the Santa Claus. So we've got 3 hours for Bailey, for Chloe, for a Santa Claus. So 3 hours here, 4 hours here, and these are hours. There we go. Okay, so what are the times available? I don't know. It says here that if neither one wishes to work more than 20 hours per week, how many snowmen and Santas must they make to maximize their income? Well, listen here, guys. Use your logic. If neither one wants to work more than 20 hours, that means they want to work less than 20 hours, or less than or equal to 20 hours. And that's the time available in hours. So the key word is neither. They don't want to work more than 20 hours, means they want to work less or equal to 20 hours. And that goes for both of them. All right, so we translated the problem. Now we need to define our unknowns. We don't know how many snowmen. It says how many snowmen and how many Santas should they make? Well, let X be the number of snowmen here, number of. X equals number of, not of. X equals number of snowmen. Let Y equal the number of Santa Claus. So X equals number of snowmen, and Y equal to the number of Santa Claus that they're going to make. Okay. Once you define your variables, then you can kind of translate what in the world's going on here. So here we go. This is the tough part for most students. All right, we've got to take our time, because they have a limitation here, or a constraint. This is our limitations, or what we call constraints to the problem. That's the term they use in linear programming. We've got to translate those into inequalities. So we need one for Bailey and then one for Chloe. Okay, so Bailey's time limitation. Let's see. It takes her 4 hours for each snowman, and 8 hours for 2, 12 hours for 3, and so on. So in general, you got to take your number of hours for each snowman and multiply it by how many you have. So in this case, you want to take the number of hours 4 per snowman and multiply it by how many you're making. In this case, we're making X. Okay, so we have 4X hours just for the snowman. We got 3 times the number of hours Y for the Santa Claus. So plus 3Y here. That's got to be less than or equal to 20 hours. Once again, if there's 4 hours needed for a snowman for 1, 8 hours for 2, and 12 hours for 3, you're multiplying the number of hours per snowman by how many you have, and the number of hours for the Santa Claus by how many you're making, which is Y in this case. All right, and all that's got to be less than or equal to 20 hours, because that's the maximum time available. Okay, they don't want to work more than 20, so they want to work less than or equal to 20. These are in hours. Now, Chloe has a limitation or constraint too. So Chloe's time, this is Bailey's time. Let me see. She only takes 2 hours to make a snowman and 4 hours for a Santa Claus. So it takes longer for her to make a Santa Claus, but less time for a snowman. So for 1 snowman, 2 hours. For 2 snowman, 2 times 2 is 4 hours. For 3 snowman, it's 6 hours. For 4 snowman, it's 8 hours. But in general, it's 2 times the number of snowman. So 2x for Chloe plus 4 times the number of Santa Clauses, which is y, and that's got to be less than or equal to 20 because she doesn't want to work more than 20 hours either. So she wants to work less than or equal to 20 hours total. Of course, this number of snowmen and Santa Clauses cannot be negative, so we got our non-negatives, which means either 0 or positive. So x has to be greater than or equal to 0. Y has to be greater than or equal to 0. And then, of course, you got to write your objective function based upon your income. You're trying to maximize the income. This is your goal or your objective. So I need to take my income that I'm making and write in an objective or goal function. All right, so we know that there's $80 per snowman. So for 1 snowman, we make 80. For 2, it's 2 times 80 or 160. For 3, it's 3 times 80 or 240. But in general, it's 80 times the number of snowmen. So 80x, this is going to be an income function here, I for income, and that's going to be equal to 80 times how many we're making, x, dollar sign here, it's money, plus 64 times how many Santa Claus we're making, which is y. So 64 times y here. We want to maximize this. We want to get as much money as possible, so we want to maximize. Okay, so what we need to do now is graph the system of constraints. All right, we got to solve for y. So I'm going to do that here. I'm going to call this inequality 1 and this one 2, like I always do. I get 4x plus 3y is less than or equal to 20. I'm going to subtract 4x. I get 3y is less than or equal to negative 4x plus 20. Divide by 3. I get y is less than or equal to negative 4/3 x plus 6 2/3. All right, 20 divided by 3 is 6 2/3. Or 3 into 20 is 6 2/3. Here's your slope. Here's your y-intercept. Now, before I graph, I look at the other one. I got 2x plus 4y is less than or equal to 20. After subtracting 2x, I get 4y is less than or equal to negative 2x plus 20. Divide by 4 on everything. Simplify, and you get y is less than or equal to negative 1/2 x plus 5. So already I see my slope here and a y-intercept here. So at this point, what you want to do is start graphing. The y-intercepts are small, 6 2/3 and 5. That's no big deal. I have enough room. So I'm going to say that this is this 2, 4, 6. 2, 4, 6. I'm just labeling these.
Irish to the reception desk.
Sorry about that. I'm still at school. All right. So now we start graphing. So let's graph the first inequality at 6 2/3, which is between 6 and 7, obviously. So you divide the unit up into 2 equal parts. That's 6 1/3, and that's 6 2/3. So right there is 6 2/3. So I place a point there. All right, and then you got to go down 4, right 3 from that point. So put your pencil at 6 2/3 and count down 4 and right 3. So down 4. 1, 2, 3, 4. 1, 2, 3 to the right. All right, 1, 2, 3, 4. 1, 2, 3 to the right. So down here. Get your straight edge out and make a nice clean line. All right, so there we go, right about there. Okay. Now the less than or equal to, that means it's solid and below. So we use the arrow technique and shade below. I'm going to label this inequality number 1. All right, now the second inequality. I'm going to switch to blue, starting at 5. There's 5 right there. All right, down 1, right 2. So down 1, right 2. Oh, I already have an intersection point right there. Down 1, right 2. Down 1, right 2. Keep doing that. Repeat it many times. See your line. Take a straight edge out. Draw a nice line. Okay. At this point, well, we got a shade here. So it's less than or equal to, again, right here. And so therefore it's below. Use the arrow technique. And then label that number 2 for inequality 2. Now you're non-negative, so I'm going to switch to green. Remember, this one here is a vertical boundary line. Okay, all x values that are greater than 0 are lying to the right of 0. If that's 0, then 1, 2, 3 are obviously greater than or equal to 0, so it lies to the right. This is x greater than or equal to 0. You saw this in previous lessons, 5, 6, and 7, so this should sound really familiar. And then y greater than 0, that's a horizontal boundary line. All right. Y is equal to 0 here. Here's 1, 2, 3, 4, 5, and guess what? They lie above. So these y values are up right here. All right, y greater than or equal to 0. You look at your previous lessons. We've done this in every single lesson for the past 2 weeks. All right, lies above. Okay, where do they all meet? Where does the black, the blue, the green, and the red overlap? All right, that's called the feasible region, and it intersects in here. They all intersect in through here in this polygon. All right, so let's shade this in and see what we've got. So this is our feasible region. It's called the feasible region in linear programming, and in other words, it's the solution region. Okay, but what are the vertices? A, B, C right here, and D. So A is up 5 units, that's at 0, 5. B, it's right 2, up 4, so 2, 4. C is right 5, so 5, 0. And then D is the origin, so D is 0, 0, which is really not a solution because that means you make nothing. 0 snowman and 0 Santa Clauses, which you don't want to do that because you're trying to maximize something, so you got to build something, guys. So really, D is a non-solution. Okay, I'm really looking at A, B, and C. Which one of these maximizes my income? All right, so we got to take these values and bring them over here like we always do. A is at 0, 5. B at 2, 4. C at 5, 0. And I'll write down D just for the heck of it, but it's not going to be a solution. And we're trying to maximize the income function, so which is 80x plus 64y. We got to take our vertices and bring them in. Substitute in. So I is going to be equal to 80 times something plus 64 times something. All right, you got to understand that x is 0, y is 5. So understand that the first coordinate is x and the second coordinate is y. So put your x and y values in. Anything times 0 is 0. And so on the first one here, the income is equal to, let me see, 60 times 5 is 300, times 4 times 5 is 20, so 320. So $320 for the first one. At B, the income is 80 times 2 plus 64 times 4. That's 160 plus 2, 256. That's a total of 416. When you add, for the third one, it's 80 times 5 plus, let's see here, got to write it correctly, 64 times 0, and that's 400. Not quite as big as 416, so it looks like 416 is the max, because on the last one, the income is 0. So I already see my max. The max income is right here. It's 416, and it occurs at point B. This is my solution right here. So I have to interpret it. What's the optimal solution? So let's highlight that. What is the optimal, optimal solution? Optimal meaning best. Well, let's see. We need to make 2 of something. Now, X stands for the number of, let's go up here, snowman, and Y is Santa Claus. Okay, so I need to make 2 snowman and 4 Santa Claus. So in this case, who are the people here? No. Okay, so Bailey and Chloe. Okay, so Bailey and Chloe. Bailey and Chloe need, all right, this is need, to make 2 snowmen, all right, and 4 Santa Clauses, 4 Santas, not Samtas, but Santas, good, there we go. All right, to maximize the income, all right, the income, which in this case is $416. All right, this right here is the solution. This is what we're looking for right here. This is what they need to do to optimize their business. They need to build 2 snowmen, it's 4 Santas. Any other combination of ornaments will not maximize their income and won't give them as much money. And that's what linear programming is all about. It's learning what to do to maximize your income or minimize cost or something to that effect, depending on the problem. All right, so what you need to do is take a look at this whole thing. Remember, this is a video here, and you need to take a look at it. Make sure that you're able to translate it into the table. Make sure you can go from table to constraints. Make sure you can go from constraints to the graph. Find your corner points. And remember that all the vertices or corner points represent the possible solutions to maximize your function. You substitute each corner point or vertex in, find the max, and then state the optimal solution and tell me what it means. All right? That's all there is to it. Give it your best shot, and I'll see you in the next example, number 5.